Good morning. Greetings from BMS College of Engineering, Bangalore. In this module, we shall see the design of FIR filters. FIR filters. Um, we know that FIR stands for Finite Impulse Response. Finite Impulse Response filters. That is the duration of the impulse response, H of n. The impulse response of the system, H of n, is a finite duration. That is, the length of the impulse response is finite. So we shall see how to design the FIR filters. Essentially, there are two major methods of designing. One is using the window method, and the next one is using frequency sampling technique. In this module, we shall see how to design using window functions. So what happens in a design, in a filter design, digital filter design? We normally go by this convention that the input to the system is and sequence xn, and output is my yn, and the system has an impulse response h of n. Of course, we are dealing only with linear time invariant systems. So this linear time invariant system has an impulse response h of n. This is in time domain representation. So I give a sequence of numbers at the input, I pass it through the system, and then I get another sequence of numbers at the output. Now, this impulse response h of n has to be of finite duration, is a finite duration, and we need to design the filter that is going to have certain requirements. Usually, filter design, the specifications are given in terms of the frequency domain specification. So h of omega. What we are given is the frequency domain specifications, and we need to now compute or design and obtain the impulse response h of n of the system. And once we have the impulse response, we can convert it to a difference equation. We can obtain the system transfer function. We can have a block diagram implementation. Of course, we can also obtain the pole zero plot. And we can verify the design by computing the frequency response of our designed filter. All these are possible. But as of now, we take the major task as given h of omega, how to obtain the impulse response hn that is going to meet the required specification. So what we have is we are given h of omega, and we need to obtain the impulse response hn. So this is our problem statement. So we are given the response or the requirements of the required filter in the frequency domain, and our aim is to now compute the impulse response of the system, which is going to replicate or have a response as close to the required specifications. So now given h of n, if I want to compute the frequency response of the system, we know how to get it. That is, this is given by say a minus infinity to infinity h of n e power minus j omega n. This is a standard expression for relating the impulse response to the frequency domain representation, and we also know that the system transfer function h of z is given by n equal to minus infinity to infinity h of n z to the power of minus n. These are we are aware of these expressions. That is, given the time domain representation h of n, we know how to compute the frequency domain representation. But and we also know that this is Z transform. There is one more significant property that we are all aware, that h of omega, the frequency domain representation of any discrete time sequence, is periodic. And has a period of 2 pi. So this is something we are aware for. So any discrete time sequence, Hn, if we compute the frequency response of the system h omega, it is periodic, and the period is 2 pi. This is applicable for all discrete time sequences. When I move from the time domain to the frequency domain, this becomes an important property now. Now we shall take a small deviation, we shall take a small deviation. That is, we shall try to look into the Fourier series representation. What is Fourier series representation? If we recollect, if I have a continuous time, periodic signal. I have a continuous time periodic signal, and say period being t naught, and hence the angular frequency omega naught is, say, given by 2 pi by t naught. Then the Fourier series gives us that we can represent this signal x of t as x of n e to the power of j omega naught n t. What is this? This is a statement. This is the Fourier series representation, or this is also known as the exponential Fourier series. Of course, we can also have the equivalent another method of representing the same Fourier series as the cosine Fourier series, or the trigonometric Fourier series, where we represent in terms of sine and cos. All can be converted from one form to the other. Let's take this exponential Fourier series. So a periodic signal. See here, in Fourier series, we are not moving from one domain to the other. The left hand side is also a function of time, and the right hand side is also a function of time. The Fourier series, so what it gives us is, the Fourier series gives us an exact representation of periodic signals. So I can represent any given periodic signal in terms of the Fourier series coefficients. Of course, the signal needs to satisfy the Dirichlet's conditions, and once it satisfies the Dirichlet's conditions, we can have the Fourier series representation of the periodic signal. And here x of n is known as the Fourier series coefficients, and is given by 1 by t naught integral over t naught x of t in one period e to the power of minus jn omega naught t dt. So this is, so together, so I first, there is a given any periodic signal, what we need to do is, we need to compute the Fourier series coefficients using this expression, that is 1 by t naught, the period of the signal represented in any one, and this represents integration over one continuous time period. It could be 0 to t naught, it could be minus t naught by 2 to plus t naught by 2, or t naught to 2 t naught. I mean, one continuous interval of t naught. I integrate the signal x of t, and then I get the Fourier series coefficients. Once we get the Fourier series coefficients, we have the Fourier series representation of the signal, and here we have a summation that goes from minus infinity to infinity, and this coefficient x of n, and e power this summation gives us the exact representation. Now, usually for any given periodic signal, these Fourier coefficients actually decrease with increasing n. Of course, there's an exception, which is the impulse train, but otherwise, in general, the coefficients decrease, and the magnitude response is once again is even symmetry, and the phase is odd symmetric. So now what we shall do is so we shall try to use this Fourier series concept into our design of the FIR filters. So what is the concept? So now we just now saw that the so we go back to our design of FIR filters, and we have now, I have a sequence, I have the impulse response of the system Hn, and I am interested in computing the impulse response Hn for a given h omega. So this is given h omega, the frequency response is given, and I need to obtain the impulse response Hn. And now we are also aware this h of omega is periodic, and periodic with period 2 pi. So now because h of omega is periodic, what we will try to do is, so because h omega is periodic, I can represent h omega. We can represent h omega by Fourier series. By Fourier series. That is what we shall do now. So, so what we have now is h omega is periodic. So it goes from n going from minus infinity to infinity, h of n e to the power of minus j omega naught n minus j where h of n is given by 1 by 2 pi integral over one continuous interval 2 pi h of omega e to the power of j j omega n d omega. Sorry, I do not have the omega now. So now why do I have it 1 by 2 pi? Because my signal is periodic with period 2 pi, and this is my so we have just, all that we have done is we have tried to apply Fourier series concept to representing the periodic h omega. So I have my h omega in terms of h of n, which in now we can recognize h of n as two components. One, h of n is now the Fourier series coefficients. Fourier series coefficients in this representation of the signal, and h of n is also the impulse response. So h of n is the impulse response of our system, and it is also the Fourier series coefficients, and the Fourier series coefficients is given by this. So we know that to compute the Fourier series coefficient, all that we have to do is integrate over one period. That is, in this case it is 2 pi h of omega in one period, and then e power j omega. Only difference is we are normally used to having a negative sign here, so we have written it positive. As a pair, we need to ensure that we have a negative sign in one and a positive in the other. So that is the only that's the requirement that we need to ensure. So now so all that we have is, so if we redefine our problem statement, our problem statement is, given h of omega, we need to obtain h of n. And now by this Fourier series representation, we have h omega. Immediately I can get hn, and so my filter design is ready. So let us see what are the steps for designing the FIR filter. FIR filter design using the window method. So as a first step, we consider h omega, the given h omega, and we try to compute h of n. That is given by 1 by 2 pi integral over 2 pi h omega e to the power of j omega and d omega. This is what we try to compute. And then we recognize that these coefficients Hn actually extend from minus for n equal to minus infinity to plus infinity. But what is our aim? Our aim is to design, and hence by default this impulse response Hn is of infinite duration. But I am interested in designing an FIR filter which has to be of finite duration. So what I do is this h of omega, which is actually going from n equal to minus infinity to plus infinity, h of n e to the power of minus j omega n, I simply truncate it. I truncate it to going from minus m to plus m, so that my length of my FIR system is now 2m plus 1. So I is my by Fourier series representation, we have the exact representation when I have infinite Fourier series coefficients. And we also know that these coefficients Hn in general decrease with increasing n. So the strength of these Fourier series coefficient decreases as we increase n. Using this property of any Fourier series coefficients of any periodic signal, now we take the liberty of truncating it to some reasonable length. So we take it symmetric, so minus m to plus m, and then I have a finite duration impulse response. So that's it. So and how does this happen? This is happening because I am actually multiplying by when. How does this happen? Because my infinite duration impulse response, my same design filter, I'm actually multiplying it by a window function, say a rectangular window function, which is given by 1 for minus m less than or equal to n less than or and 0 otherwise. So when I do this multiplication, my impulse response, which extends over minus infinity to plus infinity, I'm multiplying it by a window function that extends from minus m to plus m. So I'm making it a finite duration. And once I multiply, I now have that's it. I now have my impulse response Hn, which actually extends from minus m to plus m. So this is of length of finite duration length n, which is given by 2m plus 1, and my filter design is complete. So I've got the coefficients. Now if I try to sketch my impulse response n, what we have is we are going to have it from minus m to plus m. And we know that whenever and all other values are going to be 0. So we have forcefully truncated it by multiplying it by a window function of unit strength for range minus m to plus m. And so this infinite sequence Hn of infinite duration, we have made it a finite duration because we are interested in designing an FIR filter, that is finite duration impulse response. And once it truncated, now we will immediately recognize that this design of h of n is actually a non-causal system because we have impulse response being present even for n less than 0. So as the next step, what we shall do is whatever we have designed Hn, we just shift it. We just shift the entire sequence to the right by m, and then I'll have all zeros, and then I have some non-zero values up to from 0 to n minus 1, and again I have all zeros. So I give it a right shift. I give a right shift of my design sequence Hn, right shift by m values, and then I have my final design. So this completes the design of the filter. So given any h omega, I evaluate that integral, compute Hn, then I truncate it to some finite duration, and then I shift it to the right by m, and we have a causal response. So this completes our design of the filter. So now next step would be to test the design. How do we are given h omega, we have implemented, and then we got Hn, and h of n, and let us say my final design. After following all these steps for that meets all the given specifications, it turns out to be say h0, h1, h2, and so on up to h of n minus 1. So I shift it to the right, and I have this, and and because of the symmetry of the Fourier series coefficients, what we will observe is there will be an even symmetry in the coefficients. That is, h0 will be equal to h of n minus 1. h1 will be equal to h of n minus 2. There is an even symmetry in the coefficients. The first one equal to the last one, and so on. And this symmetry ensures that the phase response is going to be linear. This even, we'll see this later, but for now we take it that this even symmetry in the designed filter coefficients ensures that the phase response is linear, and the linear phase response is always desirable because we get an undistorted transmission through the filter. So this completes our design, and I have the coefficients of length n given by 2m plus 1. So now how do we test the design? So to test the design, all that I have to do is I have to compute h of omega for this design system. So I have my n going from 0 to n minus 1, h of n e to the power of minus j omega n. I need to just compute the frequency response h omega, and once I evaluate this summation, I will get the frequency response of my designed filter. And depending on whatever length and what is the size of our window function, we are going to have a deviation from our desired response. And as we increase m, the accuracy, or we are going to have a better representation of the design filter. So this simple step will help us test our design. And having designed it, now comes the implementation part. So if we need to implement the filter. So one method of implementing is by the direct form representation. So I have my impulse response h of n given by h of 0, h1, h2, and so on up to h of n minus 1. So all that I need to do is I have my input x of n, and I will have a lot of delay elements, and these can be recognized as the branch gain, and this is my output yn. So I multiply the first value by h of 0, this by h1, this by hn minus h2, and the last value, because of the symmetry, this is also going to be h of 0, and the last one will also be h1, h0, h1, and so on, because of the symmetry in the coefficient. So this is a direct form implementation, wherein we are going to have the number of delay elements is going to be n minus 1 delay elements, and then we have adders and multipliers, and then so we have n multipliers, n minus 1 delay elements, and n multipliers in implementing this FIR filter. So we have another method of implementing, which is known as the linear phase implementation of the FIR filter. What we do is here we try to reduce the number of multipliers, and we exploit the linear phase, that is the even symmetry in the input coefficients, and it goes on this way. And then I have a delay. So I am having n minus 1 delay elements. This is my input x of n, and then I have, say, my output yn. So since the gain of the first and the last element is same, what we do is I take the first and the last element and then I add them together and then I multiply it by H0. Since the second and the second last one elements again have a similar gain, I take them together, I add them, and then I multiply it by the gain H1. So this design is known as the linear phase implementation of the FIR filter, and this is an efficient method of implementation because we have in this method we have reduced the number of multipliers. And the number of multipliers is going to be n plus 1. So this is the linear phase implementation of the system. So now, having seen the procedure for FIR filter design, let's take an example. So let's take an example. Say our aim is to design an FIR filter which is a low pass filter of having a cutoff frequency say omega c, having a cutoff frequency omega c and of some length n. So this is the problem statement. Design an FIR filter, which is a low pass filter having a cutoff frequency omega c and of duration n. So given this statement, so since it's mentioned that it's a low pass filter, so what we are given is, so let's consider the interval minus pi to plus pi. So it's a low pass filter and this is the magnitude response and this is given in it's a low pass filter. So this is just translating the specifications into a plot, and since it's periodic I am plotting it only for one period, say from minus pi to plus pi h of omega, and this has by even symmetry in the response we know that it's going to be minus omega c to plus omega c, and this is translating the given specifications into a plot. So now let's try to design the filter that meets these specifications. So what happens is, as my first step, I need to compute h of n. And what is h of n? We just saw that the Fourier series representation is given by this. I need to, because it's periodic with over 2 pi, 1 by 2 pi integral h of over 2 pi h of omega e to the power of j omega n d omega. This is the specifications, and in this particular example of a low pass filter, what happens is 1 by 2 pi, my limits of integration is now translates to minus omega c to plus omega c. So minus omega c to plus omega c, and h omega it's of gain say 1 and e to the power of j omega n d omega. And then I get, so e to the power of j omega n by j n, and the limits of integration being minus omega c to plus omega c. So this I can, so I continue evaluating say 1 by pi n. I just for convenience say I take it this way, and e to the power of my omega is now omega c, j omega c n minus e to the power of minus j omega c n divided by 2j. So I have a 2 here, a pi and n remain here, and so now this quantity within the bracket we can immediately recognize it as the as sine omega c n, and I'll keep, say I multiply and divide by omega c, and this is what I have. I have sine omega c n, and then I have pi n, and I multiply and divide by omega c. So this now becomes omega c by pi sin omega c n. Okay. So this completes our design. This is my h of n. that for a low pass filter using a window function evaluating the integral, we get h of n as omega c by pi sinc omega c, and depending on omega c we can compute the actual coefficients hn. And we know that when if we try to plot h of n, of course it's just taking some I mean the sinc function, we know that it's a sine wave that keeps on reducing in magnitude as increasing n, and so this is what we have hn, that is of infinite duration. As the next step, I'm going to multiply it by a window function. Second step, so having done the first step, the second step, we are going to multiply it by a window function that is going to be of length minus m to plus m, and all of strength 1. So when I multiply this, I'm going to get a finite duration impulse response. So then I get, when I take the product h of n into wn, I'm now going to get my since it's multiplying by 1, I have the same coefficients retained, and depending on whatever m we select, we are going to get the result. So this is my step 2. I take my rectangular function, window function, and then I multiply. And the next step, what I do is, as my step 3, I'm going to give a right shift by m. So this is going from minus m to plus m. I am going to give a right shift by n to make the whole response causal. So I'm going to have, say, this is my filter design that goes from 0 to n minus 1, and all other values being 0. This is my final design, or my designed filter h of n. So this completes the design of the FIR filter, of the low pass filter. So, and we have the design. So next, suppose I want to test my design. All that we have to do is just compute h omega for n equal to 0 to n minus 1, and this is my design filter hd of n and e power minus j omega n. Once I evaluate this and try to plot the frequency response h omega, I will know how good my design is as compared to the required design specifications of a low pass filter with a cutoff of omega c. And we can also implement the filter using the direct form 1. And coming to the implementation, I can implement it by the two methods, either the direct form representation, or using the linear phase implementation. Because we know the coefficients of the impulse response Hn are going to have an even symmetry in the values. So we can implement it in either of the methods. So this is as an example, we have considered a low pass filter. And we can also convert it to the system transfer function, or the pole zero plot, etc. So now let's take one more example, which is going to be a designing of a high pass filter. So let's take as a second example. So let's take the aim is to design an FIR filter, which is a high pass filter, and which has a cutoff frequency, say pi minus omega c. The cutoff frequency is say pi minus omega c. So now this is of length n. So once again, our aim is to design an FIR filter of length n, which is a high pass filter. So if I want to translate these specifications, and if I try to plot, because only then I get comfortable in doing the integration. And instead, now, just for convenience, we know that it's periodic with period 2 pi, and I have the freedom of taking my limits of integration either from minus pi to plus pi, or 0 to 2 pi. In this case, we shall take the interval from 0 to 2 pi. And what we are given is the cutoff frequency of the filter. The high pass cutoff is given as pi minus omega c. And hence by symmetry, this is going to be pi plus omega c. So this is the specification that is given. So let's try to implement this high pass filter. So once again, our step one would be to compute the Fourier series coefficients given by 2 pi h of omega e to the power of j omega n d omega. And by looking at the desired frequency response of a high pass filter, we recognize that in this case, my limits of integration is going to be pi minus omega c to pi plus omega c. And once again, my desired response in the pass band is, say, constant omega n d omega. So what does that make it? So 1 by 2 pi and e power j omega n by jn, and limits of integration being pi minus omega c to pi plus omega c. And this makes it h of n equal to 1 by 2 pi. My numerator now becomes e to the power of j pi plus omega c n minus e to the power of j pi minus omega c n a whole divided by jn. And this can be, I'll just do a little bit of rearrangement, say 1 by pi n, and I can take e to the power of j n pi out, and then what I have is e power j omega c n minus e to the power of minus j omega c n divided by 2j. I've retained my pi here, I've taken the n here, I've taken the 2 within, so this is what. And now this whole quantity, e power j omega cn minus e power minus j omega cn by 2j, we can recognize it by the Euler's identity as sine omega cn. So what we have is e power j n pi sine omega cn divided by pi n. Now once again, I will multiply and divide by omega c. So then what I have, this quantity sine omega c n by omega c n, we recognize it as the sinc function. Sinc omega c n. And once again, I have my omega c by pi. And e power j n pi, again we'll recognize it as minus 1 to the power of n. So we have a very interesting result. So we have h of n of the high pass filter given in this manner with the cutoff. Of course, we need to recognize that my cutoff of the high pass filter is pi minus omega c to pi plus omega c. That is actually pi minus omega c, but because of symmetry, we have it this. Or for specifications, it is just pi minus omega c. And if I compare this result with my earlier result, which we got for the low pass filter, we had omega c by pi sinc omega cn. This is an extremely interesting result because comparing equations 1 and 2, what we find is if I have a low pass filter designed for a cutoff of omega c, I can get the coefficients or the impulse response hn in this manner. Whereas in a high pass filter, we have exactly similar, only difference being alternate terms are negative. For n equal to 0, it's positive. For n equal to odd, it is negative. So all odd number coefficients are going to be negative, and even number coefficients going to be positive. This is an extreme, like in analog filter design. Suppose I have designed an analog a low pass filter. I have a filter which includes a number of resistors and capacitors. I need to convert the low pass filter to a high pass filter. We just interchange the resistor and capacitor. The same filter now becomes a high pass filter. Exactly similar in the design of discrete digital filters. I can convert a low pass filter to a high pass filter by changing the signs of the alternate terms by using this important result -1 to the power of n. So this is the first step, computing the coefficients. And the second step in my FIR filter design, the second so this is my filter after multiplying it by the rectangular function. And as the final design, I need to give the right shift. My step 3 will be give a right shift by n by n. And so we have the designed filter. This is a filter which is a high pass filter of length n given by 2n plus 1. So this completes the design of the filter. Once again, we can verify the design. We can check for the design how good our design is by computing the frequency response h omega for and this is the way to test, and we can implement the design filter either using the direct form representation or using the linear phase representation. So we will stop here for this module. In the next module, in the next module, we shall take up actual examples. Examples for designing a low pass filter and a high pass filter. We'll take specific cutoff frequencies, we'll implement it, verify the design, and we'll also see what happens, what is the effect of m. I mean, how is the design of the filter when m is small, or what happens when I increase m. If I increase m, what is the effect of increasing m, and is the rectangular window good, or is there any need for going in for other window functions, is what we shall take up in the next module. And for reference for this module, I have referred to the book on digital signal processing by Rabiner and Gold. Thank you.